Hi again. Today we will go through a third solved problem in the chapter magnetic field due to current. If you want to go through interactive tests, please log in to our website. The problem here is a bit tricky. There are two parallel straight wires which are very long, both of which are perpendicular to the plane of the paper or the screen. The distances between wire A and wire B is given. In the case of wire A, the current is going into the plane of the paper as shown by the cross. In the case of wire B in blue color, it's not sure whether the current is going in or coming out of the plane of the paper. There is a point P where the magnetic field is defined as 0, and even if it's not stated in the problem, we have to assume that A, B and P are in a straight line based on the sketch that they give out there. So P lies on the straight line joining A and B. That's what I meant to say. There's a point S out there in space where the distances are given, and we have to find out the magnetic field at the point S, and also we have to find out the force per unit length on the wire B. For the wire B, there are only two cases possible for the direction of current. As seen on the left, I have taken a case where the current is going into the plane of the paper for the wire B. In this case, if we apply the right hand thumb rule for both the wire A and wire B, you can see that the direction for the magnetic field will be clockwise as per the curled fingers. And then the magnetic field of the wire A will pass through the point P as well. So you can see the arrow there. The magnetic field of the wire B will also be clockwise and pass through point P. The direction of arrow will be the same. So that means that the point P will experience a double magnetic field. So it can't be 0. Therefore, it's obvious that the right hand sketch will be correct, where the current flowing through the wire B has to be coming upwards out of the plane of the paper. Only then the clockwise magnetic field of the wire A will be compensated by the anti-clockwise magnetic field of the wire B. Now let's find the magnetic field at the point P and make it 0. That means that the magnetic field due to the wire A, which is B1, is getting exactly compensated by the magnetic field B2 due to the wire B. Now let's apply the general formula for the magnetic field. That's B is equal to mu 0 by 2 pi into I by D. For the point P, it's at a distance of 2 meters plus 10 by 11 meters from the wire A. So plug that for D in the denominator. In the numerator, you have the current I, which is 9.6 amperes. It's given in the problem. So we get B1. For the anti-clockwise magnetic field at point P due to the wire B, we have the magnetic field B2 is equal to mu 0 by 2 pi into the current flowing through wire B, which is I. We don't know that yet. And the distance is just 10 by 11 meters from wire B to the point P. So equating this, we will get I is equal to 2.999. We can take it as 3 amperes. Next, let's find out the magnetic field at the point S, which is hanging out there in space. The point S will experience a clockwise magnetic field vector due to the wire A and an anti-clockwise magnetic field vector due to the wire B. So let's call it B1S and B2S. B1S will be again mu 0 by 2 pi into current flowing through wire A, that's 9.6, divided by the distance from wire A to S, which is 1.6 meters. So you will get that. Similarly, B to S will be mu 0 by 2 pi into the current flowing through wire B, which we just found as 3 amperes, divided by the distance from B to S, which is 1.2 meters. So we get B to S. And below that, I have drawn a sketch to make it very clear on the directions of the magnetic field that are passing through the point S. There are two magnetic fields passing through the point S. We now have to find the resultant magnetic field at the point S, both in terms of magnitude and direction. Of course, we can't add the magnetic fields algebraically, B1S and B2S, because they are pointing at 90 degrees to each other. And still, we might get stuck here unless we use some trick. So we have to look at the dimensions of the distances between A, B and S. AB is 2 meters, B to S is 1.2 meters, and A to S is 1.6 meters. Now try squaring them and you will get 2 squared is equal to 4, 1.6 whole squared is 2.56, and 1.2 whole squared is 1.44. And then suddenly we can see that 4 is equal to 2.56 plus 1.44. That is 2 squared is equal to 1.6 whole squared plus 1.2 whole squared. This forms a right angle triangle. And here the distance 2 meters is the hypotenuse. So immediately draw the triangle on the bottom right corner, and then you can see that the magnetic fields B1S and B2S also will be at 90 degrees to each other. Now we have the angles between the magnetic field vectors. Having done that tricky thing in the previous slide, now it becomes easier. And if you see the sketch on the right hand side, you have the two vectors B1S and B2S, which are perpendicular to each other, and you have the resultant vector BR, which we have to find out. And BR squared will be simply B1S whole squared plus B2S whole squared. So plug in the values, and as you can see step by step, you will find that BR squared is equal to mu 0 by 2 pi whole squared into 42.25. At this stage, we have to be careful about mu 0 by 2 pi. So mu 0 by 4 pi is that famous constant 10 to the power minus 7 Tesla meter per ampere. So therefore, mu 0 by 2 pi will be 2 into 10 to the power minus 7. So plugging that, you will get BR is 1.3 into 10 to the power minus 6 Tesla, or 1.3 micro Tesla. We can also find the angle for the resultant. So tan theta will be opposite side by adjacent side, that is B2S by B1S, and therefore theta comes out as 22.78 degrees, which looks very reasonable considering that B1S is much bigger than B2S. So this is just a quick visual cross check that we have got the right direction. The net force in the wire B due to wire A can be found by the general equation F is equal to L into mu 0 by 2 pi into I1 I2 by D. Therefore F by L will be mu 0 by 2 pi into I1 I2 by D. Plug in the values for mu 0 by 2 pi. I1 is given as 9.6 amperes. I2 we found out as 3 amperes. The distance between the wires is 2 meters, and therefore we get the force per unit length acting on wire B as 28.8 into 10 to the power minus 7 newtons. In fact, it's the same force that will also be acting on wire A as well. So we have the answers to all the questions that have been asked in the problem. Trust you found this video useful. Have a great day. If you have any questions, write back to us. Thanks.